want to talk a little bit about the de Broglie hypothesis. And what this hypothesis states is essentially that anything that has mass is also going to exhibit a certain amount of wave-like properties. Okay? It means I pick up Ted and I throw Ted across the room. Ted is going to exhibit a wave-like property according to de Broglie's hypothesis. Okay? Essentially, he came up with this idea of a standing wave, and he took the idea of a guitar, right, and used a guitar to illustrate what a standing wave was. Okay, as a guitar string is plucked, it's going to vibrate at a certain frequency, generates that sound that you hear from guitars. Okay, and the general idea is that because of a wave's nature, all right, the wave is going to behave a lot in a certain way associated with the circle. So if I take a circle and I divide it in half, okay, what this means is that at a certain point, if I take the bottom of this thing and I move it to the other side, what I've done is I've generated a wave. So the waves that we are accustomed to seeing, okay, this isn't the best drawing in the world, but it'll work, all right? The waves that we're associated with seeing, the top and bottom quadrants or hemispheres of the wave both exhibit a part that's above the wave, and I'll say that's a positive section, and a part that's below the wave. And at certain points, you're going to run into areas where the wave crosses a certain line, and it doesn't look like it has any amplitude above or below the line. These locations are known as nodes. Okay? So if I take a guitar string, right, and I pluck the guitar string, depending upon how it's vibrating, I might see a standing wave that looks like this, right? And what that is half of a wavelength, because this is a full wavelength. If I did it this way, my end value, this value would be 1/2, okay, because I'm not showing a full wave. If I pluck it again, right, pluck it a little harder, and I see something that looks like this, my end value is going to be equal to 1. All right, if I pluck it again, right, and I get this, and in this case it's 3/2. Now, de Broglie noticed that when you're dealing with electrons, right, in the quantum area, you're not going to be able to get to these half electrons, right, these half values. So anything that did not produce an integer for n is a forbidden transition. So this one and this one would be forbidden in the quantum sphere. Okay, we can't see that. What de Broglie then did was do some mathematics that's associated with it, right? And he came up with an equation to state that all matter will work so according to this particular equation. And what this is wavelength is equal to mass, or h, over m times u. Okay? Now you know what the wavelength lambda is. H is Planck's constant, m is mass, and u, in this case, is velocity. Now, whenever we deal with Planck's constant, though, we're dealing with joules. So remember, anything that's in mass has to be reported in kilograms. Okay? So mass has to be in kilograms. Speed in general, or velocity, is in meters per second. Planck's constant's in joules. Remember, joules has that kilogram squared over second squared term, and that will help cancel out any of the second squared or kilograms that you run into. Okay, excuse me. So that's what you end up with the wavelength. Okay, that's how you get to that particular term. In my class, I'm just going to show you what this equation is. We're not actually going to work it, right? And there's a couple of other equations we're not actually going to do examples of. But I do want to show you that de Broglie did have an impact on how we perceive electrons in an orbit. And those electrons in that orbit, they can't have half values for these n values. Everything has to be an integer, which is why de Broglie's hypothesis is important for quantum mechanics. All right. right, the next guy who is important in the development of quantum mechanics was Heisenberg. Heisenberg, okay, actually a scientist, not a guy on Breaking Bad. It's actually based off a guy, Heisenberg. Now, Heisenberg came up with this thing called the uncertainty principle. All right. Heisenberg's uncertainty principle deals with a lot of calculus, okay, and basically boils down to any sort of particle with mass as this. So this delta x times delta or m delta u. Okay. Whoa. No, wrong. Not equal to, but is greater than or equal to h over 4 times mass. No, 4 times pi. There you go. So here's Planck's constant again. And we've got mass and we've got change in speed. And then x here is the change in position. You look at this thing and you're like, wow, that's a pretty fancy equation, Dr. I don't know if I can do that. Don't worry about it, okay? This is something that you can get to and start working with in PCAM. Heisenberg's uncertainty principle basically was a little bit of a rebuke to Bohr's model, okay? Not so much a rebuke as sort of a fine-tuning, because in Bohr's model, everything went from 2 to 6. 2 to 6, 2 to 6, 2 to 6. And if that was the case, electrons would always follow the same path around a nucleus. Heisenberg looked at this and said, I'm not really sure that's the case because there's a lot of different things that are affecting that electron. And Heisenberg just stated that the electron's path is generally going to follow what Bohr said with a certain amount of wiggle room. So with a 95% confidence, we know where the electron's going to be. To give you an analogy, if Heisenberg was a racing fan, like a NASCAR fan, okay, what he'd say is that, okay, for the most part, this is the center of a racetrack, okay? Here's the electron racetrack, okay? And terrible art skills, okay. So that's the center of a racetrack, because the nucleus, right? This is the racetrack where the racing occurs, right? And for most of the race, we're going to say that the electrons are going to be within the confines of that track. So 95% of the time, the electrons are within the scope of this track. So the electrons are flying around here at a certain point in that particular quantum level. Okay, n is equal to 2, or n is equal to 4, something like that. We know that 95% of the time the electron is within that time. Now, in the racing world, we know that there are times when the car comes over here for a pit stop before it goes back into that track. Okay? There's a certain amount of time where that electron is not there. And in being not there, it is outside the realms of Bohr's predictions. That's the uncertainty principle. Most of the time, the electron's on the track. There's a certain amount of time where that electron is not on the track, where it's off the track, or it's doing a pit stop, or the opposite happens, okay? Or the electron goes flying off into the crowd, okay? Here's the electron flying off into the crowd, and here's some racing fans, running for their lives, okay, away from the electron, okay, and this guy is spilling his beer, there's his beer spilling all over the place. And he's scared because the electron is moving at a highest rate of speed, right? Because the thing, it doesn't have a lot of mass associated with it. But that's the general Heisenberg principle at that point. All right, and one more thing of what I'm talking about. We talked about uncertainty, I talked about de Broglie, now we're going to talk about Schroedinger. Schrodinger's equation is kind of a mix of those two, and he came up with something called the wave function. The wave function, identified as psi. It's not a pitchfork, it's not Poseidon tried it there. This is psi, and what this is this is the wave function. And the wave function is it's something that's brought to us by calculus. It can't be brought to us by simple algebra. We've got to use calculus to define a wave function. I'm not going to try to define what it is here. That's something that you can explore in PChem if you want. But I am going to tell you what the outcome of the Schrodinger equation is. And the Schrodinger equation simply states that it's more of a confirmation that every wave function that's associated with a particle that has mass and its wavelength, okay, like an electron. Each one of these has a certain path in an atom that can be defined by a wave function. And a way of looking at that is that if you've got a pathway where the electrons are moving, so here's a nucleus, right? The places where you're going to have the most probability of finding electrons, and that's what the wave function shows, is where the light path is. So in this case, I'll do dark paths as I'm using a whiteboard. So it's low inverted, but the darkest spots is where you'd expect to see where that electron is. Okay? So the darkest spots is where the electron is, and as this becomes lighter around the outside, there's a lower probability of finding an electron within those. Okay? So there's a lower probability of finding an electron within these things. Okay? Until you get to a dark area, the probability of finding electrons, those, drops to a very, very low percentage. Okay? And that's what a wave function is. So instead of thinking about an atom, okay, if you think about an atom where you've got these electrons which are zipping around like this, that's nice for basic artwork, but it's not really an accurate representation of where the electrons are. Because it turns out to be more of an average and more of a prediction of where that electron is based upon what other external properties are happening. Because if you think about it, if you got more than one electron, as these things are orbiting a nucleus, they're going to run into other electrons. What happens when two negative charges get close to each other? They're going to repel. So the pathway of an electron is not entirely guaranteed by what happens in the Broglie, or excuse me, by the Bohr model. However, the Bohr model does show us the basics idea that electrons are built into specific levels. And those specific levels, even though the level is a little bit fuzzy, each one of those requires a certain amount of energy to promote that electron from one spot to another. And that allows us to build and identify what electrons are in any particular atom. So this is the quantum model of how electrons work on the atomic scale. Okay?